Hi, everyone. Welcome to lecture 3. And this lecture, we're going to be talking about kernel regression, which is a way of using nonlinear models to fit data, although it is a very simple extension of linear regression. And just before we start covering the fundamentals of this method, let's just begin with a review of what happened in the last lecture. So in the last lecture, let's start with this review. We talked about linear regression. And we introduced it in the context of using it to solve some very standard machine learning problems. And in particular, we sort of considered this class of functions as it was one of the simplest things we could try out. And so basically, what is linear regression again? So remember the visual picture. In one dimension, if I have some feature x and I want to predict some labels y, and I'm given a set of training samples here, my goal was to find initially a line of best fit to the data that minimized these residuals, the square error to each of these points. And how did we exactly do that? Well, we were given a training set of data points, xi, yi. This is I equals 1 to n. And this was our xi's were in d dimensions. These were d-dimensional features. And our yi's were some real value labels. And what we wanted to do is we wanted to find an estimator that we could use to predict future samples, x, what the value y would be. And the way we did this is we just minimized a loss, which was the square loss on our training set. And we considered this simple class of linear models. So models parameterized by this factor, w. Okay. And how did we minimize this loss? We used gradient descent, and we observed that if you initialize gradient descent with the initial value w not equals 0, we get this minimum norm solution. So w hat was this minimum norm solution given by the pseudo inverse here. So yx pseudo inverse. And here, of course, x is just this giant matrix of concatenated vectors xi. In particular, remember, we rewrote the loss in terms of this big X as follows. So here, x, just to recall, is just a concatenation of these xn's. Okay. So now, this is, of course, a very, very simple class of models. I think in practice, in occasion, you can actually get some pretty decent baselines with just linear regression. Although for many data sets, like anything related to text, maybe, or images, or something high dimensional, usually there's some nonlinear trend in the data, and we want to try to extend this class of linear models to something nonlinear. And so that'll be the goal of the lecture today, is to try to do something like that. And so let's actually, before we do something crazy like try neural networks, let's consider the following simple extension. So let's now move from linear regression to kernel regression. And what is the key idea here? So we're going to actually want to keep our class of functions restricted to this linear class in some way. But what we're going to do, instead of changing this class of functions to be nonlinear through the parameters w, we're going to actually apply a nonlinear transformation to our data. And this is sort of the key idea, where we're going to take our data, apply some feature map to it, and then solve linear regression in this transformed space. And in effect, this is a nonlinear model. And one way we can think about this is as follows. So here's the key idea. So instead of transforming, instead of changing parameterization to be nonlinear, what I mean by this is instead of changing my function w to be something like w phi of x, phi of w2x, something like that, I'm just going to apply a feature map to my data. So instead, transform the features xi nonlinear. Okay. And in particular, what we're going to do is we're going to consider now our class of functions. It's still going to be this class of functions from Rd to R. But what we're going to do now is we're going to say f of x, instead of being w times x for some fixed w, we're actually going to consider it as the inner product of some w and psi of x, where psi is now the transformation. So psi is just a function from Rd to a space H, which has an inner product. So what is H? It's going to be a vector space with an inner product. And we're going to say it's complete. And because this is not an analysis class, or I don't expect you to know functional analysis for this, just think about it as a space with some inner product. It's actually going to be called a Hilbert space. But we'll just keep it as some space where you can compute this inner product for now. Okay. So let's now think a bit. This is all pretty abstract. Let's give some examples to see exactly what's going on. Okay. So for the first example, let's consider you have a data set that looks as follows. So these examples are going to kind of motivate why would you want to apply some nonlinear map first and then fit a linear function? Why is this at all beneficial? So let's say you have data that looks as follows. I'm going to have data that lies along two concentric circles in d dimensions. And here what I'm plotting is I have, let's say, two features. It's just the x1 and x2 coordinate of these data points. And now what happens is I have two sets of classes here. I have the data points on the inner circle, which I'm going to give class label 1. So I'm going to say these points, class label +1. And these points, class label -1. I'm just giving +1 and -1 as examples. This could be some indicator for maybe dogs and cats. So +1 could be dogs, -1 could be cats, and let's say x1, x2 are some features of dogs and cat images, and this is how the features look. Okay. So the issue is if I want to use a linear model to somehow separate, I want to draw a line to separate the red and the blue points, I cannot actually do it in this space. So no matter how I draw a line, there's always going to be some red points to the left of the line, some blue points to the left of the line. There's going to be a mixture. I can never perfectly separate out these two. On the other hand, what I can do is do exactly what I said with this feature map. And what I'm going to do is apply a feature map psi. And psi is just going to introduce some information about the radius of the circle that these points lie on. And how do I do that? I'm actually just going to keep x1 and x2 as the first two features. And in the last feature, I'm just going to write out square root of x1 squared plus x2 squared. Okay. Now, if I apply psi to every single one of these data points, shown in blue and red on the left here, what is this new space going to look like? So I'll have my x1, x2, x3. I'm still going to have the two circles based off the x1 and x2 axes. But now I've encoded this on this x3 axis. I've encoded this radius information. So points on the red circle are going to look somewhere like this. They're going to be around this x3 axis, just a slight positive value. But now the points on the blue circle have a much bigger radius. So they're going to be higher up in this space. So I'll have a circle that looks like this up top. And I have a circle that looks like this a little bit lower. Now, if I ask the same question here, what happens if I want to use a linear model in this space. I want to draw a plane that separates the red and the blue circle. That's actually quite easy. I have a whole bunch of space here. I can just draw a plane. Everything above this plane is class -1. Everything below is class +1. So you see there's naturally some benefit if I've transformed my data in the right way to a higher dimensional space. So here, psi was this map from R2 to R3. We transformed our data to a higher dimensional space, used a linear model, and actually we're able to perfectly generalize. We got the pattern down exactly. And so at this point, the question is, there are some cases for sure where this will work. We just saw one. The key idea though is how do you pick this feature map? So maybe I'll take a moment now and write out a couple of questions that you might have at this point. So 2 questions. 1, what kind of feature map psi should I use? Okay. And the second question is, what if the space H is huge? In fact, what if it's infinitely dimensional? And recall, what is the space H? So H is just psi is taking your RD, d-dimensional data, and mapping it to H. And so keep in mind, what we're effectively doing is transforming the data and solving linear regression in this space. Now, linear regression in d dimensions, we just required we had d parameters. If we're solving linear regression in a space H, if H is infinite dimensional, this is kind of like having infinitely many parameters. This kind of seems like an intractable problem. So I think the big surprise with kernel regression is that definitely we can solve the second problem. That one's actually very tractable, and we will cover that today. The interesting thing, though, is that the first question is a very intricate question. And in choosing this feature map appropriately, we'll see that there's kind of a couple of ways to get around this. Maybe we don't even need to consider feature maps. We'll consider things instead called kernels. The other idea is that the other cool part about this course is that a lot of this course is going to involve selecting and designing kernels that work well on general data sets. So the whole idea is that we're going to build up the kernel regression framework, connect it to somehow neural networks, and then use kernels based on neural network architectures. And this will give us some impressive performance on a lot of tasks. So let's for now ignore the first question in some regard, and let's focus on this second question, just to make the kernel regression framework clear. Okay. So in order to solve kernel regression in this Hilbert space, in order to solve linear regression in this space H, what are we actually going to do? Well, there's a couple of theorems that we need to first establish and look for some invariances in our linear regression analysis that can extend to any space. And so what we're going to start with is something called the representer theorem. And just keep in mind, all of this stuff that we're doing now, all of this analysis is just to understand how to do linear regression when this space H is huge. If H is not a huge space, if H is like RD+1, you could just use linear regression. Just the standard thing we did in the first lecture, and you're good to go. And in fact, if it's finite dimensional and not very large, you can always do this. So the key will be figuring this out for a large space. Okay. So before we get into what this representer theorem is, let's go back to the analysis of linear regression and identify some key things, some key points from this analysis. Oops. So recall, in linear regression, we use gradient descent to minimize this loss. Okay. And one thing we saw, remember the gradient descent updates, they looked something like this. We had WT plus 1 is WT plus eta y minus WX X transpose. Okay. And then we rearranged this equation as follows. Great. So now there's an interesting point in this analysis, which I think we discussed last time, but I just wanted to make it a bit clearer. So if we start out with some, and at any point, if we have some W naught, we started out with W naught being 0, but in fact, this was just, we can write this as a sum over I equals 1 to n, alpha I of 0, xi transpose. And in this case, the alpha i's were all equal to 0. Okay, so why are we doing this? Well, it turns out if you have that at any point, your W at time t is a sum of training examples, these training examples, and some linear combination of them, this property always holds through linear regression. So at any point time t plus 1, at any point time t, you're going to find the following. Your predictor is always going to be a linear combination of training examples in this way. Great. And why is this interesting? Well, if this holds throughout training, it kind of has to hold at the end of the day, and this implies that the solution that you get by solving linear regression here is going to be a solution that lies in the span of the training example. So your solution is going to be, at the end of the day, some linear combination of your training examples. And this is the key idea of the representer theorem. So what do we want to do? We want to be able to find an invariant like this and show that we can find a solution where the solution is in terms of a linear combination of the training examples. Why does this help? Well, you see that now, while this term here has d parameters, this is in terms of the dimension of the features, we've somehow transformed it into finding the alpha i's, of which there's only n of them. So now we have somehow n parameters. And this is the magic of the representer theorem. Instead of solving linear regression in this space with d parameters, we transform it into a space where you only have n, where n is the number of the training examples. So if H is a huge infinite dimensional space, it doesn't matter, because n, the number of examples we have, is always finite. And that's the problem. Those are the parameters that we want to estimate. Okay. So now let's go into the kernel regression framework. In general, what we're doing is solving linear regression in this transformed space. Okay. So now our loss instead looks something like this. Yi, inner product W, and psi I. Psi of xi, where psi is our feature map. And this inner product, if I drop the script, it's always in this space H. So forgive me if I drop the script occasionally. But now we're going to try to solve linear regression in this space. And so it turns out that one can prove the minimum norm solution in this space. So before we had the minimum L2 norm solution in the space RD for linear regression. Here we have this minimum H norm solution. So this is just the norm induced by the inner product here. Minimum H norm solution is going to have the property. So it's going to have the property that W star is again going to be this linear combination of training examples. It's going to be some alpha I psi of xi. And here, note, I don't use the transpose because I'm taking these inner products. So I'm assuming this is some element of the space H. And while I've written down the proof of this in the notes, I don't want to go through it because it's a little bit technical, and I just kind of want to give the intuition in the lecture as to where this is coming from. And for those who are kind of interested more in the math and the rigor of this, I encourage you to check out the lecture notes and go through the proof. The proof is not so different from basically what we've done here above. If you've already proved in the homework that this is somehow the minimum L2 norm solution, so this is the min L2 norm solution, you're basically using somehow the same ideas to prove that the corresponding one is the minimum H norm solution, and that if you have any other solution, you can do some orthogonal decomposition into this W star plus some term, and it shouldn't affect the loss in some way. Okay, but this is sort of the key idea of kernel regression. And again, I want to just emphasize that while W is an element of the space H, W can have infinitely many parameters. This is just some element in an enormous vector space. But now we have found a way to parameterize it by n parameters. And this is exactly what we're going to want to solve for. So let's just rewrite what happens. Let me copy this over. And let's just substitute in what happens if we assume that that's the right form. Oops. Let's see here. Okay. So we have our loss. We have our solution there. We have some property of the solution that we care about. So let's just rewrite what happens if I just plug this W star in. Okay. So I'm just going to rewrite. Instead of W, I'm plugging in this W star. This is just I equals 1 to n, alpha I, psi of xi. Let me actually subscript this a little different so the indices don't get confusing. Okay. And let me actually just call this J's here. Okay. Okay. So now it's kind of clear. So what we're going to do is just the standard trick with the inner product. We're going to use linearity of the inner product to expand out some of these terms. So this is just I equals 1 to n, summation j equals 1 to n, alpha j. I can even pull this out. It's j psi of x. Okay. Great. So now it becomes clear, in order to solve this, this is starting to look a bit more like a linear regression problem. And in fact, we can even write it this way. So let's just start grouping some of these terms. What does this actually look like? We have our yi. Instead of writing this as a sum, I'm going to recognize this as a product of two giant vectors. Alpha 1. So I'm going to write out the vector of alpha n. And then here, I'm just going to write out the giant vector of inner products. So it's psi of x1, psi of xi, psi of x2, psi of xi, and so on. And we have psi of xn, psi of xi. Now it's this giant thing squared. And does this inner product make sense? So just to sanity check what we've done, if I just look at the first term, when I equals, let's just look at for one I have an alpha 1 times psi of x1, psi of xi. And that's exactly what I have here. When j equals 1, I have an alpha 1, psi of x1, psi of xi. And when j equals 2, I get the corresponding alpha 2, psi of x2, psi of xi. And so things do work out. Okay, great. So now this is really starting to look like a linear regression problem. And in fact, we now have these parameters alpha, which is just some 1 by n vector. And now I have these new transformed examples, which are n by 1 vectors. And this is for every xi, I have some vector like this. I mean, maybe we can call it. What I'm actually going to do is call it x. And I'll explain in a minute why I'm writing it like this. xi, comma x. Okay. Actually, let's pick a better notation. Let's do psi of capital X, comma xi. Great. Okay. Now, here's the key insight from doing all of this. We've kind of rewritten this problem. It's 1 to n, yi minus alpha k of x, xi squared. This is a vector in Rn. This is a vector in R1 by n. And everything seems to be good. Now, here's the trick. What we've done is, in order to solve linear regression in this space, we just need to know how to evaluate these inner products. And this is going to be what is called the kernel trick. So we need to know how to compute psi of xi, psi of xj for any ij in the set 1 to n. And if we know how to do that, we know exactly what these vectors k of x and xi are. We're good to go. We've transformed it into linear regression. This is something we know how to do from the second lecture. Okay. So now let's actually take a moment and abstract away this computation. And this is where we're going to start introducing the notion of kernels. And so the whole idea is that for any 2 points, x and x tilde in Rd, we're just going to define the kernel here as the thing that we want to compute. It's just this inner product of psi x and psi x tilde. Okay, so this kernel has to have some properties. In fact, let's even abstract away the inner product notion and just define what it means to have a kernel function here. So definition 1. Okay, so this is going to be very, very general. Given some non-empty set x, the kernel is a symmetric continuous function. Oops. And we're going to denote it by k. And it's just taking 2 elements of x. And for now, we're going to consider mapping this to a real value. Okay. Of course, this doesn't help us too much. This is quite abstract. We already know that for some cases, the kernel that we're caring about is induced by an inner product. So we have this k of x, x tilde is the inner product of 2 things. And inner products have to have some property that, you know, that introduces some constraints. And one of those constraints, for example, is that if we look at k of x, x tilde, or k of x and x, just the same vectors, in our case, this is going to be an inner product of psi of x, psi of x. This is just going to be psi of x squared. And so this is non-negative. So we can't just have some arbitrary symmetric continuous function. There's some extra constraints that we need. And in fact, the exact constraint that we need is going to be here. This is going to be the definition of a positive semi-definite kernel. So I'm going to just rewrite it out formally again. So given a non-empty set X, a positive semi-definite kernel is a, it's of course the symmetric continuous function, but let's actually say this function k is a positive semi-definite kernel if and only if, now this is a bit of a complicated condition, but we'll see it's actually a bit easy to verify in some cases. For I equals 1 to n contained in X, and for any constants ci contained in R, we have the following constraint. Summation I equals 1 to n, summation j equals 1 to n, ci, cj, k of xi, xj is greater than or equal to 0. So somehow for any set of constants, any set of n data points, we need to ensure that this sum is non-negative. And this is a tricky condition to verify. One thing that we're actually going to prove, and I'm going to give this as an exercise, but maybe I can give some hints on how to do it here, is that this is written as proposition 2 in the lecture notes. But just to summarize, if you have a kernel function, let's say rd to r, that is given by an inner product. So let's say k of x tilde is inner product psi of x tilde in some space, then k is a positive semi-definite kernel. I'm going to abbreviate this as PSD. Okay. And now, why is this true? Just to give a quick hint. Okay, let's consider the case. Let's just try to verify this condition. Okay, and let's try to verify the condition in definition 2 when n equals 2. So how will we do this? Well, we'll have to pick some constants c1, c2, and we'll have to pick some data points x1, x2. Okay, so let's just write out what is that sum. It's a sum over 4 terms, and those terms are exactly c1, k of x1, x1, plus c1, c2, k of x1, x2, plus c2, c1, k of x2, x1, and c2, c2, k of x2, x2. Let me write this on the next slide. Okay. And by the way, this is always a good strategy. Anytime you see a complicated problem with a lot of notation, the first step should always be, let's substitute some very small values and let's try it out from there. And this tends to pretty much always give some good insight into how to go about doing this problem. Okay, so let's just simplify some things here. So I have this is just c1 squared, x1. Let me actually already start substituting in here. I know this is psi of x1, plus c1, c2, and c2, c1. This is a symmetric thing. So these two terms better be equal. So I'm going to get 2c1, c2, inner product psi of x1, psi of x2. And then lastly, I'm going to get a c2 squared, psi of x2, psi of x2. Okay. Now, I don't know about you, but this is starting to look a little bit suspicious. I'm starting to see something that looks like a c1 plus c2 whole squared in there. And in fact, this is also a norm of psi of x2 squared. And this is a norm of psi of x1 squared. So I'm guessing that this is going to be some quadratic polynomial here. And in fact, it is. It's exactly going to be norm psi of x1 plus c2 psi of x2. It's going to be this thing squared. Great. Now that we've written it in terms of a norm squared, oops, sorry, this is not the 2 norm, this is the h norm. Now we know that norms are always non-negative, so we are good to go. So at least for the case where n equals 2, we're good to go. We found the right thing. And I would really try extending this to the case where you have n examples next, and that will be the homework assignment. Okay, but now this is quite easy. So if all we care about are kernels, which are defined by some inner product, we are all set. We know that this kernel will be positive definite. I should also mention that there's other conditions like Bachner's theorem, which are a little bit more complex, which will help you understand, which is technically an easier condition than this thing here for verifying if something is positive semi-definite kernel. Okay, so right now we've just defined this very abstract notion to get around computing these inner products. But let's actually give some examples of some kernels now. And this is just some classical kernels that have been around for many decades. So let's go over some examples. And in the homework, actually, there's one question that will ask you to prove that some of these are positive definite, semi-definite kernels. And the trick is to find the feature map. So in general, that's a pretty hard thing to do, but in these cases, it's not so bad. So of course, we have the first example is the linear kernel. And this is just k of x, x tilde, is just x transpose x tilde. Why is it called the linear kernel? Well, at least one easy way to remember why it's the linear kernel is that if you plug this in and you try to solve that optimization problem from a few slides ago with this kernel, you'll be exactly solving linear regression, and you'll get back this solution y x dagger, which is the Moore-Penrose pseudo-inverse solution. And I encourage everyone to try writing that out exactly in detail and seeing that you do get this linear solution here. Now, here's one that I think is very popular, but unfortunately does not work it's not the best one, I have to say, in practice, but for some reason it is just extremely popular. And this is the Gaussian or RBF kernel. And this is RBF stands for radial basis function, but I always just call this the Gaussian kernel. And actually, if you look in libraries like scikit-learn or any of the popular libraries for doing kernels, this is always in there. This is always also the default option. You'll always see RBF appear as the default option, which is a bit troubling, I think. And you'll see why through the homework and experiments. But this kernel is just e power some parameter L times the difference in norm between x and x tilde squared. And this is for some positive L. You can take some positive real value. Okay. Of course, if you take, instead of L being positive, if you take L equals 0, you'll get 1 everywhere. This thing will just give you, as you'll see, it'll give you a training gram matrix of all 1s. This is kind of useless. So you want to take L to be something positive. Now, here's what I think is one of the best kernels. If you were going to try out kernel regression, this is the kernel that I would recommend you try first. And this is the Laplace kernel. And for those of you who are maybe a little bit ahead in the course or are familiar with a lot of this material, this Laplace kernel is actually very, very similar to the NTK on vectorized data. And so both of them are very, very competitive. And I would say it's like probably the best kernel to try out first, just because of how simple it is. And here's the remarkable thing. The Laplace kernel is basically at least the way we're defining it, is the same thing as the Gaussian kernel, except you drop the square in the exponent. And this is somehow way more robust to the choice of parameter L. Okay. And before we go into how these kernels perform, I just want to go back and tie up the story of, if we're given a kernel function, how do we actually solve regression in this Hilbert space? And let's just make this very, very clear. And this is going to be called kernel regression. Okay, and we'll put it as a theorem because it's important in this space. And it's pretty important to make sure we understand this theorem completely, because it's going to be the foundation for the rest of the course. So all we're going to basically do in the rest of the course is come up with different kernel functions based off neural networks and see that these kernel functions actually work quite well in practice. Okay. And I'll put a star here, and we'll call it, this will be kernel regression. And I'm going to write this out a bit formally. Okay. So let H be, I'm going to use the word Hilbert here, Hilbert space, but again, just think it's a space with this inner product. Inner product. Okay. And now let psi be our feature map into H, and let K be a kernel function. Be a kernel function such that K of X and X tilde is exactly psi of X tilde. Okay. Then the minimum, I'm just going to abbreviate it as min, H norm minimizer of the loss. So what is all this notation? This is just basically saying, what are we doing? We're solving linear regression in this transformed space. We just have a bit of overhead when writing this notation, when we're writing this statement. But it's basically what we've said so far. Okay, so we're minimizing this loss. The minimizer we saw is given by W star. Remember before we wrote it in terms of these alpha i's, we're now actually just exactly going to solve for what that alpha I is. And in particular, it's going to be given by something that looks a bit familiar, which is, it looks like this Gram matrix. But these are our coefficients. These are these alpha i's from the previous few pages. And so here, what we've shown, what we're claiming is that the minimum norm solution is again in the span of the training data. And what is this K hat? So where K hat is a positive semi-definite matrix with entries K hat of ij is just K of xi, xj. So this K hat is typically called the Gram matrix. And now for those of you who are interested in what does this predictor look like, so if I'm given a new data point and I want to predict something, the corresponding predictor is given by this f hat of x, which is just y k dagger, k of x, x. Okay. And here, the last thing to note is this k of x, x is just a giant n-dimensional vector. And k of x, the ith entry, is exactly k of xi, x. Great. So this is quite a heavy theorem, but a lot of the work is already done for us. And let's just parse a little bit. So the predictor here. So let's parse a little bit what's going on in this statement. Okay, so we're trying to solve linear regression in this high dimensional space. We're given a way to abstract out the relevant inner products by the kernel. Okay, and now we're going to use this trick from before, writing the fact that the W star has to be a linear combination of training examples. We're going to solve for these alpha i's. And we're claiming that that vector of alpha i's is somehow just the thing here. It's just that big vector alpha equals alpha 1, alpha 2, up to alpha n. We're claiming that thing is just y k hat. Sorry, there should be a hat here. We're claiming that that thing is just y k hat dagger. And this looks a little bit familiar to linear regression. So remember, in linear regression, what did our predictor look like at the end of the day? It looked like y x dagger x. So you see there's somehow this parallel. We have a yx dagger here. In kernel regression, we have some yk dagger here. And then instead of x, we have a k of x comma x. And what's actually happening here? Why are these extra terms introduced? Well, the reason is that we had to somehow account for transforming the data to a higher dimensional space. We were using the feature map first, psi, and then solving linear regression in the space. And so that's why we have these nice parallels. Let me just make this clear. So this is linear regression. We had this nice parallel. Okay. So the proof, actually, there's not much left to do. Because of the representer theorem, we already know that we're solving an optimization problem that looks like this. So let me make this a bit clear. So by the representer theorem, we already know that the loss function looks something like this. Remember, we transformed it in terms of the alpha i's, and we already ended up writing it like this. Where, keep in mind, this vector here was just this vector of inner products, so psi of x1, psi of xi, all the way down to inner product psi of xn, psi of xi. Okay, and this was our Rn vector. And now I think hopefully it's become clear why I used this notation before, because this is exactly what we're going to have to do for a new data point in the predictor. It's exactly this function that I wrote down here, this k of x comma x. Okay. So now let's just write this in our usual block form. Right now we've written it out as a sum of these n examples. But we're just going to use linear regression to solve for these alpha i's. And I'll also change it so that the loss, instead of being in terms of that w, that Hilbert space vector, it's now just over these alphas. This is a finite dimensional vector. So now this is just going to be y minus alpha k. And I'm going to call this k hat. So what is k hat? Well, remember before for linear regression that x, we were doing y minus wx, and capital X was just a concatenation of all the vectors x1 to xn. Now it's a concatenation. K hat is just a concatenation of these vectors. So if I'm to write it out, it's going to look something like this. It's a concatenation first, where the I equals 1. So here in the first row, I would equal 1. Psi of x1, xn, x1. Okay. And similarly, we go all the way down. We'll have a psi of x1, xn. Oops. And then here we'll have a psi of xn, psi of xn, inner product. Okay. So now this is great. It turns out that because of the symmetric property, this is exactly the same matrix that I wrote before. So note k hat is symmetric because of the symmetry of the inner products in the space. I should mention we're only going to be considering ones which have the symmetry property, not conjugate symmetry. But either way, the coefficients are 1, so it's fine. So we have the symmetric property. And so we have that k hat of ij is exactly our kernel. It's exactly k of I, xi, xj, which is given by that inner product. Great. Okay. So now we know how to solve a system of equations like this. Now we're good to go. So if we want to minimize the loss, right here, this is just a linear system of equations. If I want to find alpha that solves this, well, I just get alpha. In fact, it's even better. It's a square system of equations because this is an n by n matrix. So I can even just solve the system alpha k hat equals y. I can just do the usual inverse thing and get that this is y k hat inverse. Now, the reason I put a dagger here instead of an inverse is that sometimes based off the kernel, you could have a positive semi-definite matrix. It's not required to have all positive singular eigenvalues here. So I'm just going to leave it as a dagger. But basically in practice, for many applications like the radial basis function kernel or Laplace kernel, you'll see that this is sufficient. You can actually just take the y k hat inverse and you can be good to go. Okay. So now we're good. We've solved for the alphas, but keep in mind that the representer theorem actually told us that the solution to kernel regression is the summation of a linear combination of psi of xi's, where you have alpha I as the coefficients. So now, if I actually want to get a predictor, what does my predictor look like? You can't just do w star times x, because this is not like linear regression. You transform the data first, right? So the predictor, remember, is going to be inner product of w star and psi of x. And so let's just substitute everything in. Well, you have that f hat of x is just summation I equals 1 to n, alpha I, psi of xi, psi of x. And remember, this is now just this giant vector alpha times all of those inner products. Okay. And now if we plug in what we know about alpha from here, we get that this is exactly y k hat dagger k of x, x. And this is the solution to kernel regression. Okay. So I know this was a lot of math. This is a bit of a grind of a calculation to get through this. But remember, linear regression was also a grind to get through and find out that we got the minimum norm solution. But now here's the best part. Just like every method in this course, once you know how to do it theoretically, implementation is super easy. So how do we actually implement kernel regression? So last time, I know it was kind of funny to see you have your implementation of linear regression is literally one line. We're going to have a few more lines here, but not that many more. So I'm going to call this now empirical connection. I guess there's no demonstration other than me drawing here, so let's do that. There is a nice demonstration of kernels in general in the lecture notes, but let's just go over how to code this. Okay, So now, let's say you're given a data set. So you're given x, y, and let's say you're given a kernel function. So I'm given for any pair x, x tilde, I know what this value is. I have a function that tells me what the value is. Okay. So how would I code this? Well, the first step, let me write it here, is I'm going to compute the training kernel matrix. And this is just going to be k hat. And remember, this is an n by n matrix. And k hat of ij is just the function k applied to example I and example j. And you can compute this in whatever way you want. There's vectorized ways of doing this in NumPy, so you don't have to waste a lot of time for looping through everything. And we'll give many examples of how to do this. So great. You've now got your training kernel matrix, which is n by n. Now, this is the tricky part, I think. There's many, many ways to solve kernel regression. The simplest one by far is to just use the solve function in NumPy. And what you're going to do is you're going to solve for your alphas. And basically what this comes from is you solve the system of equations. Alpha k hat equals y. And make sure to use the NumPy solve function, not pin. And why? Because solve is way faster, and solve is meant for square matrices, of which you have a square matrix here. It's an n by n matrix. This is the coolest part about kernel regression, is that you don't have to even worry about this. In the best case, you can even just compute the inverse. You can just compute inv of k hat. But okay, so let's go ahead for now and use the solve function. Now the third step is you want to be able to predict. So given a new sample x, the predictor, so your prediction f hat of x is going to be, I take my alpha yk hat inverse or yk hat dagger, and then I just compute. So compute first k of x, and remember that this is an n-dimensional vector where the ith entry is just k of xi, x. And now you just plug that in here, and you are good to go. That is it. So you should effectively have 3 lines once you have the kernel function. Compute the training kernel matrix, compute this alpha, and then predict. You compute maybe some extra vectors with this k of x and x, and you just predict. So this is the best part. After all of that math, it's just kind of 3-line implementation. Very little can go wrong. The only kind of thing I can see going wrong in this is that the kernel matrix, this definition of the kernel, maybe there's some trickiness in implementing that in a vectorized way. But that's more of a software implementation issue. If you just want to do it using for loops, go ahead. That's totally fine. It'll be a bit slow, but so be it. At least you'll have a solid, non-buggy implementation of kernel regression. Okay, so let's now consider some practical aspects of kernel regression. So maybe the first thing I want to mention before I go into some examples of how the pictures will actually look if you try to use kernel regression. The first thing is that kernels kind of have this negative connotation that you're solving a square system of equations. This is going to take quite some time if your kernel matrix is, let's say your number of examples is like 60,000. So note, if n is, let's say, 60,000, in the traditional way, k hat is going to be a 60k by 60k matrix, and you're going to have to solve the system with this. That's actually kind of feasible, although it's very slow. It's going to take you like several minutes to do this. I mean, if you go to 100,000, good luck. I think you're going to be there for hours, if not days, depending on your hardware. But here's the nice trick. In the past decade, actually just a few years ago, there's been a lot of work on solving kernel regression very efficiently on the GPU. And this you're actually going to have some experience with in the homework. One of the libraries is called EigenPro. And how does EigenPro work? For those of you who are familiar with some optimization tricks, at a high level, this is how EigenPro is working. So in neural networks, it's very rarely the case that if you have 60,000 examples, you compute gradients for all 60,000 and use vanilla gradient descent. The trick is that when you're minimizing this loss, when I'm trying to solve the system k hat, the first thing that I can note is that I actually don't need to compute k hat up front. I can do this in batches and use something called stochastic gradient descent. And for those of you who are not familiar with this, don't worry about it for now. It's not super important for the rest of the course. You can stick with just solving the system of equations. But this is just for those of you who are curious about this extra aspect of how to do this efficiently. And basically what stochastic gradient descent is going to allow you to do is instead of computing k hat entirely, you compute just a subset of columns and you optimize, you compute gradients for this set of columns and you minimize the loss in this way. The next thing is that instead of using stochastic gradient descent directly, EigenPro computes something called a preconditioner matrix, which makes sure that when you're solving kernel regression, it converges fast along certain directions of the data. And this is what really makes EigenPro super fast. So if I'm trying to solve, and I kid you not, I've had many examples of students who've worked with me now, who I always say this, and I think they take it as kind of a joke, like this is him being sarcastic. But no, if you have a data set that has 60,000 examples, EigenPro regression should literally take you 3 seconds. I would give it, depending on your hardware, maybe 3 to 10 seconds on the GPU. And if it's taking longer than that to give you like 0 loss on your data set, something is wrong. It could be that you chose some parameters wrong, but this is the kind of speed that we're talking about. And later on in the course, we'll actually have some work that shows that you can use EigenPro to solve kernel regression on super high dimensional problems. We're talking about 500,000 training examples to 1 million training examples. And there's some nice images that come out of that. Okay, so this is the first practical note that I had. The second kind of cool thing about kernel regression, so this, I'll just call this is a note on fast kernel regression solvers. Okay, so this is note 1. The second note, which may be of interest for people who are interested in some kind of interpretation of what's happening. So keep in mind that from this equation, one thing that's actually kind of difficult to do with neural networks is interpret why are they making a certain prediction in some way. But this is not the case with kernels. In fact, something becomes very clear with kernels. Your output, because you have this vector y here, it's always a linear combination of labels of training data. So you're just taking a giant, I think ideally this will be a vector. If you have multi-class, you're going to have something else here. But if you just consider the case where y's are real valued, you'll see that your prediction is exactly this linear combination over training samples. And this big vector here that I've highlighted, this will tell you how much each example gets weighted in this linear combination. So I wouldn't say this is complete interpretability, but it's a step up than what you would get with neural networks. I can at least tell you why a kernel regression model made this prediction, and I can tell you which examples in particular were weighted very heavily in this prediction. And this is quite a nice aspect. This gives some reasonable level of interpretability to say, okay, I know now that my model is doing this because maybe there's an example that's close by in this space that's having a similar label. Okay. So I'll call this mild interpretability, because it's not the dream of, the neural network is going to tell me exactly how it's making a prediction, or a machine learning model tells me exactly what it's doing, but it's a step up. It's a step up from what you would get with most machine learning models. Okay. So now we have the last point, which is in the last lecture, we gave a nice example of just what visually linear regression looks like. Although I guess it's a bit trivial in that it's just a line of best fit. But now we're going to show what kernel regression looks like, at least visually. And let's just do this for the Laplace kernel, which I think is one of the best kernels out there for people who want to try stuff. So let's say again, you have a set of data points. And I'm going to space them out a little bit for now. Okay. I should mention a couple of things here. Unlike the case of linear regression, where it's possible to not achieve zero training error, because you're solving kernel regression in a huge space, for most of these kernels, it's an infinite dimensional space, you're able to solve this system of equations exactly. And that means that you always interpolate the training data. That means you achieve zero training error. Of course, there's ways around this. You can regularize your model. You can do some tricks to make sure it doesn't perfectly fit the training data. But I think what we'll see is a large part of this course is that perfectly fitting training data is somehow a good thing. And models that fit the training data perfectly will also typically generalize well. And this is one of the big emerging trends and kind of surprising findings of the past decade. And we'll get into that a lot more in the next lecture. But for now, we're just going to use kernel regression, where we just fit the data exactly and see how well it does. So let's consider what happens when we use the Laplace kernel to fit this data. Keep in mind, we had some features x here and some values, some labels y. And what is the Laplace kernel? It's just for any 2 points. I have e power negative L, norm of x minus x tilde, without the square. And that's the key thing. Okay. So now, what happens if L is super small? So if L is like let's say L is like 0.01, something like that. Actually, let me write it in red so that you all can see how the curve will look. Okay. When L is super small, the Laplace kernel actually has an interesting shape. And I encourage you all to try varying values of L and see how it looks. But when you take L to be very small, what you'll see is that it actually does something where it just simply connects the dots and keeps going. Here, it keeps going like this. So it does this very tight interpolating solution where it doesn't waste any space going outside of this range of the training data crazily. And what I mean by that is, in contrast, you could have a function that interpolates the data that looks like this. It looks very crazy. And this is what they typically say is overfitting. So it means that you found a function that fits your data points exactly, but somewhere along the way, it's like too constrained and it goes away from the data points too much, and so it has high test error. But this is not the case with the Laplace kernel when you have a small l. In fact, in most cases, and we'll see this through the homework, and you can even try doing Laplace kernel on things like MNIST or CFAR10 or any image data classification task, you'll see that for small bandwidth, it actually gives you some pretty decent performance. But of course, we'll get into kernels that do much, much better on these image classification tasks than something like Laplace kernel. Okay, so the other regime I wanted to mention here is what happens when L is super large. So let's say L is like 1,000. Okay, I know because of the property of my kernel, for any pair of samples, let's say I just look at xi, this thing is going to be exactly e power 0, which is 1, Okay. Now for any xi, xj, which are not training samples, this is like e power negative 1,000 times something. This is going to be a very, very small value. So e power like negative 1,000 times some constant. This is going to be very small. This is going to be close to 0. So what does that mean for my kernel regression? So in kernel regression, remember, my predictor was the inverse of this Graham matrix, this k hat, and then k of x, x. Okay. So now what does this matrix look like if my L is huge? Well, on the diagonal, it's going to be all ones because that's what we were given here. On the off diagonal terms, it's just approximately 0. So this is k hat, looks something like this. So it's approximately 0 everywhere else. So this matrix is super close to the identity. And when I invert it, it's going to look like the identity. Okay, so k hat dagger is going to be like the identity. And now this is quite nice. What does k of x comma x look like? Well, unfortunately, this new sample x, unless it's one of the data points, k of x, x is going to be a vector that's very, very close to 0 everywhere. So if you're far from any training sample, it's definitely going to be like numerically 0. Otherwise, it's going to be close to 0. So now how does that function look in practice? Well, what you'll see is something like this. It'll spike up at the data points, and it'll be very close to 0 everywhere else. And so this is probably why you wouldn't want to pick a super high bandwidth. So right here, by the way, these two things imply that f hat of x is approximately 0 everywhere, or almost everywhere. Okay. So you probably don't want to pick a super large bandwidth for regression problems. And I think this is kind of at least some, hopefully, insight into how to tune this parameter L. In practice, though, a lot of libraries will just give you a default value. And I would just recommend taking something like L to be very small, something like 0.01, 0.001, all of these will be actually fine. And there's many, many more examples of this that you'll explore in the homework. But okay, so this is just a brief overview of how these things actually look in practice. And I know we went over the full derivation. What we're going to do in the next lecture, so maybe I'll do this here. So next time, what we're going to do is we're going to connect kernels and kernel regression with training neural networks. And in particular, we're going to consider neural networks that are super, super wide. So this is going to be like infinitely wide neural nets. Okay. And you'll see that the connection is actually, why are we doing this connection, by the way? The reason is that we expect that neural networks, they have this flexibility property. This is what we saw in the introduction to the course. They're able to be applied to many, many types of data. You have convolutional nets, which are for images. You have recurrent nets. You have transformers, which are for text, also for images now. And you have a whole bunch of fully connected models and everything else going on for vectorized data and reinforcement learning in biology. So the reason we want to connect with neural nets and kernels is to give kernels the flexibility to be adapted to many of these different tasks. So the next time we'll see our first kind of almost trivial connection with neural networks, but then this will lead almost immediately into the development of the neural tangent kernel and how we can actually build kernels that closely match the performance of neural networks in practice. Okay. So I will see you all in the next lecture then, and thanks for joining me in this one.